So, hello everyone. So, today I'm going to be sharing my work about aircraft engine design from Aircraft Propulsion Class. So, my work is to design a compressor, turbine, and fan, which is turbomachinery. So, my work started at looking at the design point. So, as you can see from the report, the design point come out as the flow property at each stage, right? So I will use this property to design and turbo machinery. So to do that, we have to understand the concept of triangle velocity. Triangle velocity is basically how the flows reacts to the rotor and stator. The incoming flow will have a certain property, and when it reaches to the blades, for example, rotor, its property will change accordingly. So, as you can see from this diagram, you can use some physical relation, and we can come up with this algorithm. So, this algorithm will receive an input of the flow properties and the wanted flow properties. And we can write this algorithm into a MATLAB code, which I will show you shortly. So first, let's talk about the blade profile. In order to design a turbomachinery, we have to choose an airfoil that is designed to do such tasks. So I came up with a NACA 65A010, which is a airfoil that developed for the turbomachinery application. After that, I write a MATLAB program which computes the same algorithm that I have mentioned before into a MATLAB function, as you can see on the right. And I'll call this function in the main code, which is the optimization code that I have wrote. So it receives an input, like I said, and we set its condition, and we call the function in a while loop so that the number of stage can be optimized. So in this case, in the while loop, we call a function and the input become a new output, and the output will become the new input, which will loop for a while. And when the flow property reach the certain value that we want, the loop will break. So let's run the code to see how it looks like. So by putting the design point, we have obtained 9 stages of compressor in total with this value of final pressure. And we will use this area to derive for a dimension of the compressor, as you can see. And now we are ready to draw some CAD because we have obtained all the dimension that we need and the number of blades. Let's move on to the fan. The fan and the turbine, we apply the same logic and we can do it in the same fashion as before. So here we have obtained two number of stages, but keep in mind that in this optimization code, there might be some overshoot of the pressure because sometimes the condition that I have wrote is just if the value is higher than what we want, then it breaks, right? But sometimes it's much higher than what we want. So we have to compromise it so that the value is the closest to what we want. In this case, just one stage is almost equal to what we want. So we just use one stage of fan. And for the turbine, we have come up with a 3 number of stage in total with this final value of pressure. So now we are ready to draw some CAD. So by using SolidWorks, I can draw a geometry like this. So let me choose a section view so that you can view better. Okay, so as you can see from the geometry consists mainly of the shaft and the blades. So to model it, we need to use the dimension that we obtained from the MATLAB code and just draw it into the geometry. So let's see the shaft part. So the shaft is basically we started with 2D sketch and we use a revolve function to make it a circular shape. And for the blade, we do it in the same fashion, but first we must import the airfoil profile, which in this case is NACA 65A010. And we define the chord first and input its span, and we use a circular pattern to circularize it into the number of blades that we want. And I do this for every blade and assemble it into this assembly. So yeah, that's it for my work. Hope you enjoy it and thank you for watching.